In this video, we have the definition of an ideal. Of course, it includes left ideal, right ideal, then quotient ring and the canonical homomorphism. So first we have the definition of an ideal. A non-empty subset U of a ring R is called an ideal of R if U is a subgroup of R under addition, and for R in R, U in U, both RU and UR should be there in U. Suppose we have this alone to be true along with this condition, then we call that to be a left ideal. And if only we have this condition, then we have that to be right ideal. If both are true, then you call that to be an ideal. Next, in this lemma, we are going to have two parts. So one is, if U is an ideal of a ring R, then R mod U is a ring. So that is called quotient ring. And the canonical homomorphism from R to R mod U is onto homomorphism, or in other words, this is the homomorphic image of R. That is canonical homomorphism, that in a natural way, that is how we can define. Right, so first we have this R mod U to be an ideal. So for that we describe what this R mod U. This is similar to your collection of all right cosets, what we had in the case of group theory. So something similar to that. There we had normal subgroup, here we have ideal. Group, normal subgroup, group, we have normal subgroup, and we can talk about the quotient group. So here ring, then ideal, so you can talk about the quotient ring. So let U be an ideal of R and R mod U to be this collection. Now in order to make this collection to be a ring, we need to have two operations. One is addition, the other one is multiplication. So addition is defined in this way. We take two elements, A plus U and B plus U. So they are added in this way, A plus B plus U. We shall name this as one equation, and product is defined in this way, AB plus U. A plus U into B plus U is AB plus U. We will name this as 2. So now this being defined by us, we have to show that this is well defined. Only then we can have the closure with regard to addition and multiplication to be true. So how do we prove on this well-definedness? We'll consider two elements, A plus U and B plus U, to be equal to, say, some A prime plus U and B prime plus U respectively. That is, A plus U is equal to A prime plus U, B plus U is B prime plus U. Now we'll have to prove that it is this operation addition is actually a function. So to have this to be well defined, this is what we need to establish. A plus U plus B plus U should be equal to, that is, the elements equal should imply the images equal. This is the function. So that is what we are doing here. So A plus U plus B plus U is A prime plus U plus B prime plus U, and similarly for the product we have. Now because this is true, that implies that A minus A prime belongs to U. This is similar to your proof what you had in group theory, that HA equals HB if and only if AB inverse belongs to H. This is true if and only if AB inverse belongs to H. So in the same way, here addition is the operation. So the cosets are given by A plus U and B plus, B plus U. So that should imply, and implied by your A minus B belongs to U. So here we have, instead of B, here we have A prime. So A minus A prime should be in U. So we shall name that as some element U1 in capital U, so that you can have A to be A prime plus U1. And the same way b plus u equals b prime plus u, we can have b minus b prime belonging to u, b minus b prime belonging to u, and so you can write that as, say, some u2. So b minus b prime should be equal to some u2, so that you can have your b to be b prime plus u2. So these two will be using. So when we consider a plus b, it will be a prime plus u1 plus b prime plus u2. But we have the ring R to be commutative with regard to addition. So we have this, and from here, when we consider a plus b plus u, it will be this. Now, because u is an ideal, it's a subgroup. So, and u1 and u2 are members of u1 and u2 are members of capital U. So this will be absorbed. So you just have a prime plus b prime plus u. So this tells us that our addition is well defined. In the same way, if we consider AB, this is what we get. A prime b prime plus a prime u2 plus b prime u1. You have actually a prime, distributive law if you are using, means a prime b prime plus a prime u2, then u1 b prime plus u1 u2 plus u1 u2. So that we need to correctly write. This is not prime, this is just u1 u2. Now if you consider AB plus U, then you'll have to just replace your AB by this plus U that you have. Now these are elements of, this is definitely an element in capital U, we have mentioned earlier. Now because U is an ideal, even these two will be elements of capital U, and therefore your so U is an ideal, so that means you have this to be also present in U. So then if these are all elements of capital U, means this U will absorb them, because we studied in group theory that AH is equal to H is equal to HA if and only if A belongs to H. So the same thing for right cosets and left cosets. With that we have established that holds here also, and here addition is the operation. So we make use of this result to prove, to conclude this. So this tells us that multiplication is well defined. Now to verify all the axioms, closure as 8 axioms are to be established for a ring with respect to plus 5 axioms, with respect to multiplication 2 axioms, combined 1 distributive law. So closure obvious from the well-definedness of addition. And for associativity, we'll have to consider 3 elements. So you have a plus u plus b plus u plus c plus u. You'll have to show that this is same as a plus u plus b plus u plus c plus u. So we consider this part, and we simplify by the definition of addition. This is how it is defined. Again by the definition of addition, this is what we get. And you consider this one and simplify, you get this. So from these two we conclude that associativity is true. Now 0 plus u acts as the additive identity. Now 0 plus u is actually u only, because u being a subgroup, 0 will be present in u, and being a member of u, you will absorb that. So you have just u acting as the additive identity. Then additive inverse of any a plus u in R mod u is minus a plus u. And when we add these two, a plus u plus minus a plus u, we will get u. So this is 0 plus u, and that is our identity. That is because you have this to be a plus of minus a plus u, and that gives 0 plus u. But 0 being present in U, it will absorb, so you get this. So this acts as the additive inverse. Commutativity, we have A plus U plus B plus U to be A plus B plus U, but R is commutative with respect to plus, so you can rewrite this as A plus B as B plus A, and that in turn gives this by the definition of addition in R mod U. So R mod U is a commutative ring with respect to plus. Now, closure follows from the well-definedness of multiplication. For associativity with respect to multiplication, we consider three elements, and when we multiply these two, we get AB plus U. Multiply that with C plus U, you get this, and you have this to be AB C plus U. This, because R is associative with respect to multiplication, you have A into BC plus U. So again, by the definition of multiplication, this is A plus U into BC plus U. In between you can have one step, A plus U into BC plus U, and that in turn can be rewritten in this way, B plus U, C plus U. This one is retained as such. So that proves the associativity. Then for distributive laws, A plus U into B plus U plus C plus U, when we consider, if we add these two, this is what we get, and by the definition of multiplication, you have this. Now, because R is distributive, we can rewrite this in this way. And this again, you have AB plus U by the definition of addition in R mod U plus AC plus U. So this again by the definition of multiplication can be rewritten in this way. So that is your RHS, and in the same way you have the other distributive law, and it can be established. So if time doesn't permit, you can write one of the two and say similarly the other one can be established. So because all the 8 axioms for this to be a ring being true, we conclude that R mod U is a ring that's called a quotient ring. Now we have this canonical homomorphism. To prove that R mod U is the homomorphic image of R, you define a mapping, say phi from R to R mod U as phi of A equals A plus U. This canonical mapping is similar to the one what we had in the case of group, where phi was defined from G to G mod N. The proof is and the definition all are the same. There we had phi of G to be equal to NG, right coset. So here you have that to be A plus U. And here we don't discuss about right coset or left coset, because under addition we have R to be commutative. So R mod U is also commutative. So there is no meaning in saying A plus U and U plus A, U plus capital U plus A. So we have both of them to be the same. Now if we consider this phi being defined this way, we can show that this is well defined, and that's very obvious. Let two elements in the domain be equal, then obviously you have A plus U to be equal to B plus U, and this is nothing but the image of phi, image of A under phi, and this is image of B under phi. So this shows that phi is well defined. It's obvious that phi is onto, because the elements in this are of this form only, and that is what you have on the right side of this mapping. So we have phi to be obviously onto. For homomorphism, with regard to addition and multiplication, we have to check the condition. So as for addition is concerned, phi of A plus B, by the definition of phi, it is A plus B plus U. By the definition of addition in R by U, you have this to be A plus U plus B plus U. But this is nothing but phi of A, and this is nothing but phi of B. So you have this condition with regard to addition to be true. And as for multiplication is concerned, by the definition of the mapping phi, it is AB plus U. By the definition of multiplication in R mod U, you have this to be rewritten in this way, but this is nothing but the image of phi under image of A under phi, and this is image of B under phi. So phi is a homomorphism. Now, since phi from R to R mod U is an onto homomorphism, we conclude that R mod U is the homomorphic image of R. So in the next video, we will have the first isomorphism theorem for ideals and the second isomorphism theorem on ideals. Of course, in the case of rings based on ideals. Thank you.